So good afternoon. I'm Stephen Richardson from Howard University. Professor Henrik will have time for extended questions, both during the seminar and afterwards for people who are interested.
Hey, Mike, this is being streamed. I can take it right down after if you need to. Just put that in your pocket. It's just your slides and your voice, no camera.
Okay. All right. So just want to acknowledge two students that did most of the work I'm going to describe. All right. So I always start with motivation. Okay. And there's two motivations for this. Nitrogen, well, basically it's quantum information and sensing, and also some biosensing. Okay, and nitrogen vacancy, of course, has been a prominent leader in these fields for a few years. There's cryogenic and there's room temperature, and diamond in general has a lot of applications. So first I want to talk about motivation. So I always have long-term goals. All right, most people have short-term goals and sometimes mid-term, but not many people have long-term goals. And long-term goal is what forces me to go into fields I wouldn't go into ordinarily, and that's how you make interesting advances and interesting discoveries. So one long-term goal I've had was to replace trapped ions with a solid-state system. Okay, and what do you need for trapped ions? Well, in trapped ions, they have polarization selective optical transitions. So I like to have those. They have cycling transitions for readout. Okay, so you can get single shot. And I like to have optical control of my spin state. So I like this Raman transitions. And so at the time, I didn't know exactly what to use. As it turned out, we settled in on nitrogen vacancy, which I'll talk more about later. Basically, here it is. It turns out that nitrogen vacancy has just the right level structure. If you use the right transitions, you have polarization selective optical transitions. So you can entangle spins and photons. You have another transition that's cycling, lets you read out. Now, this experiment was actually done here at Harvard in Misha Lukin's group. And we started this around 2003, I think, or something like that. Okay, and at that time, we had no idea what the level structure of this nitrogen vacancy was. Okay, but we started it anyway, because I had experimentalist intuition it was probably going to be good. And in fact, I didn't really tell Misha that I didn't know what the level structure was. He found out a couple years afterwards. He said, wait a minute, you mean we're doing this big experiment? We're going to do this replace trapped ions, you don't even know what the level structure is? I said, don't worry about it. You know, it's a good material to start with. If it doesn't work, we'll find something better. But anyway, turns out this material was pretty much the only one for a long time. And we expected to get the spin-photon entanglement in 2 or 3 years. But it took a lot longer. And in fact, we expected to go beyond that. We expected to do teleportation. And in fact, we never even got that done. That ended up being done at Delft. And why did it not get done? Why did it take us all these years to do something that should have taken just a couple of years? And the answer is this: spectral diffusion. The line's hopping around as you excite it. After about 10 years of trial and error, okay, mostly errors, it was possible to stabilize this a bit, but it still wasn't enough to get the job done. And so what had to happen in order to make this work? What had to happen is you had to have a different color center. And the different color center was actually hidden in plain sight, as they say. This is almost as well known as nitrogen vacancy, but nobody took it seriously. And the reason they didn't take it seriously is because it had terrible optical properties. Okay, but it turns out that the reason it had terrible optical properties is because it was always looked at in really bad diamond. And so somebody put it in really good diamond, and suddenly it had fantastic optical properties. And in fact, it basically has, it has sort of the right level structure for doing these spin selective transitions. And so it ends up being really good. And in fact, if you look at the spectral diffusion, it's basically non-existent. This was also done at Harvard. We had tried to do this coupling, or basically independent sources, trying to interfere independent photon sources. We'd been trying to do this with nitrogen vacancy for more than 10 years and couldn't get it to work at all. But once the silicon vacancy was found, I guess it was brought to Misha's lab, and within a month or so, it was done. What was different? I mean, the techniques are exactly the same. The only thing that's different is the material. Okay, the color center is a lot better color center. It doesn't have the inhomogeneous sprouting, it doesn't have the spectral diffusion. So it's only a materials issue. All right, so you're working on that, and you say, well, you know, silicon vacancy is great, but it's got some problems too. Quantum efficiency is not very high, it's only 5%. So what do? You go to the periodic table. What's the next one down? Germanium vacancy. Germanium vacancy does have a good quantum efficiency. It's got the same level structure. And to give you an idea what matters, so here's a ball, basically a sill that was machined into a diamond. Here's the fluorescence from a single germanium vacancy. Here is the same fluorescence with the laser beam not blocked. Now in the case of nitrogen vacancy, we had to filter out the laser by 60 dB. And that's one of the reasons it took so many years to be able to do an experiment, because 60 dB is a big number. But here, there's no filtering at all, and you can even see something. So that's the advantage of having a strong zero photon line and a high quantum efficiency. And again, it's only the material that's changed. But of course, there are some problems. There's some instantaneous spectral diffusion, so it looks like a blinking that shows up. And of course, it's not clear whether this is due to the germanium vacancy itself or due to the quality of the diamond. As I'll show you in a bit, to get something as big as germanium into the lattice, you have to grow under conditions where you introduce a few other defects. Okay, so this was working better, so then we say, well, you know, if this works better than silicon, then the next level must work better too. So then you look at the periodic table and you say, what's next is tin, and then lead, okay? And then you start moving on down. And it turns out that you don't even have to stay on the periodic table that row. You can go to something like magnesium, okay, over there. And you get nice color centers. Tin especially was quite interesting because it had this really interesting line in the yellow, plus the one in the green. And if you excite with green, you get both. If you excite with blue, you get one, which would lead you to believe that this was a charged state. However, when you anneal at a higher temperature, this one disappears. And so you're not really sure, was it a charged state? Or maybe it was stable because there were defects. Or maybe it was a deformation in the center. Okay, but no one has really studied that. The good thing about the tin vacancy is it's got the same level structure as germanium. It's got same high quantum efficiency, but it has a very large splitting in the ground states. And if you know anything about quantum storage, it's that ground state splitting that determines the maximum bandwidth that you can store. So if you want to store a picosecond pulse, you need a terahertz. And so this has it. Okay, and then of course I told you about magnesium. That's another one. Okay, but before so basically, before I go on, I want to get into my second motivation. The second motivation is room temperature. Okay, before I got into quantum information, I had another goal. This goal was to image single biological molecules and to do it in live cells. Okay, now this was a very hard problem, but if you can solve it, there would be some advantages. Okay, and I looked around at all the different materials, and it seemed at that time that nitrogen vacancy was the best. And in fact, that's sort of guided my choice, because when I was trying to decide what to use for the trapped ion replacement, there were a couple of choices. There was rare earths, and then there was the nitrogen vacancy. But because I was thinking of eventual room temperature experiments, I chose nitrogen vacancy. And turned out that things worked in a very unplanned way. At room temperature, the coherence time was really good. We could get single shot readout, long range electron spin entanglement, and basically it's still in the lead. And that wasn't something we really expected. So sometimes you get a bit lucky. Anyway, the idea of room temperature and imaging really small things led me into super resolution. And what I found out is that the ultimate super resolution is gradient field imaging, like magnetic resonance imaging. So you go to the doctor's office, you get an MRI. That's the ultimate super resolution, okay? Everything else is an approximation to that. And so if you want to shrink it down, what do you need to do? Well, there's three steps. You got to polarize, distinguish the spins, detect. Polarization, a big magnet. On the nanoscale, you don't even really need that. Distinguish, well, you apply magnetic gradients. So it's possible to do nanoscale gradients. But the weak link is reading them out, okay? You can't read out a single radio frequency spin, just one. And so the idea was then to replace that with an optical readout. And so I was looking at a number of things and decided eventually that the nitrogen vacancy would be the first one, the good material to start with. But only to start with. I never intended it to be used very long. But to make a long story short, we did measurements where we were able to detect the spin label on the surface of the diamond. And we did the first sort of 1D image with that. Fast forward 10 years, the Chinese repeated that, where they stuck the spin on the molecule and were able to see something about on the protein, were able to see something about the protein motion. And so you look at this and you would think, well, you know, we're getting close to being able to image single molecules, but it turns out we weren't. And the reason we weren't is that this is only in bulk diamond. Okay, and it happens that between the molecule you want to sense and your nitrogen vacancy, there's a surface. And that surface can have defects, and those defects can have spins. And if they're electron spins, then they're 1,000 times stronger than what you're trying to look at, and they're a noise source blocking you. So you have to get rid of those. And again, by trial and error of 10 years, you know, mostly errors, but lots of trials, we eventually found out that you process the surface in a certain way, and you're able to get rid of most of the spins, and you can start to see things. But now think of what we got to do. If we're going to do a live cell, we got to get rid of the bulk crystal. We got to use a nanocrystal. Okay, that's where it gets really difficult, because nanocrystals are not nearly as good as bulk crystals. But then you find out biologists. So you go to the National Health Institute and you say, I want to image single molecules in live cells. You guys must need this. And you send them a proposal and they say, no, we don't need that, but diamonds are very photostable. And we want them really small so they can fit into things. We'll pay you for that. We don't need this single molecule imaging, but we do need small probes. And so yes, indeed, diamonds are very stable. Dyes bleach, quantum dots blink, but diamonds are super stable. And it turns out that they're the least toxic of all nanoparticles. You have to work really hard to find toxicity, and basically means you have to load so many diamonds into the cell that it can't do anything, can't move. Then it becomes toxic. Of course, that wasn't true with the first diamonds. They actually had a toxic coating, but in the good diamonds, that's not the case. Okay, so let me tell you more about the nitrogen vacancy and why that was so important and why it still hasn't been replaced. So essentially, you have triplet and singlet ground states. Most molecules have a singlet ground state and triplet metastable. They all have intersystem crossings. And the spin polarization happens during the intersystem crossing. In nitrogen vacancy, you happen to have a triplet ground state. There are a few others that do. And essentially what happens is you pump this transition, there's a spin selective crossing, and you spin polarize. Okay, so there's a number of materials that have that. And at first this was all done at cryogenic temperatures. Nobody ever imagined it would work at room temperature. But then one day people turned up the temperature and boiled off the helium and continued measuring. And surprisingly, they found that it didn't really depend on temperature. So it worked up to room temperature. And the nitrogen vacancy was the one they found out on. Since then, other people have looked at other color centers, and they found that some of them actually do still work at room temperature. Okay, so why haven't they all replaced nitrogen vacancy? The answer is right here. So this shows the fluorescence as a function of microwave frequency. When the microwave frequency is resonant, you're repopulating the spin. So basically, you're looking at the fluorescence in one spin state versus the fluorescence in another. There's a 30% difference, means you can tell these apart fairly soon. Okay, if this was 1 or 2%, you would have to repeat the experiment many, many, many times, and nothing that's been done with nitrogen vacancy would ever have been done. It would have been too hard. Okay, if this was much bigger, then you would have much more results than we've had so far, because you'd have easy single shot readout. You go way before where we are now. And so this is on the border. This is on the line. Okay, so far there's really nothing to compete with this, which is why it's still hanging on, okay? Later on I'll tell you that we're going to try really hard to get rid of it. Finally the NV has been more or less gotten rid of at low temperature, right, by silicon vacancy and others. But at room temperature it's still the #1, because replacements just don't get this, don't get that contrast. So let's look at what it takes to to make better diamonds. All right, this is how nanodiamonds are made now. In the old days, there was detonation. You basically take some TNT, you explode it, you scrape off these nanodiamonds from the walls. Okay, that makes really small ones, which is, the biologists thought was great, but they're terrible optical quality and they have toxic surface. And so I think everybody has finally stopped using that. There's some variations on this, like ultrasound and ablation, but they're all detonation-like techniques, and they all make similar things. Most of them are made now by bulk growth. You basically grow a big diamond of high quality. All right, so the quality is there. You squash it, you crush it all down. Well, by the time you get it crushed down, the quality is not so good anymore. And if you want to make it small, it gets exponentially hard as you get smaller. And so that's not so good for making it small or high quality. CVD growth, there's been a few experiments show you can grow good diamonds with CVD, good nanodiamonds, but it's a surface-based technique, so it's not really scalable. And just some of the biological reasons why you want small diamonds. Well, for my goal, I want to image a molecule. Molecule's about that size. Standard diamond is this size. You can sort of see it's not, there's a big mismatch. You really want something a lot smaller. And then for clinical studies, you find there's a threshold where you can get the diamonds out of the organism, which is very useful. And that happens to be around 7 nanometers. And so for a variety of reasons, you want pretty much 5 to 7 nanometers in size, and you want good nitrogen vacancies in these. And of course, there's no way to do that right now. There's also some fundamental issues. When you have a diamond with nitrogen vacancies or any color center, they're randomly placed. So you start shrinking down your diamond, you're going to find out that at some point, there's going to be 0 color centers on the average. So most of your diamonds, your nanodiamonds will be dark. And that size where that happens is 10 nanometers. But we want to go a lot smaller than that. Okay, so there's fundamental limits here. You can't get around that by tweaking your growth process. This is fundamental. You have to completely change the whole concept of growth. Quantum information, let's go back to that. Because everything works at room temperature, there was a lot of interest in making a room temperature quantum computer. So people said, let's put an array of nitrogen vacancies. They even managed to get a pair, and they coupled them and showed they could do 2-qubit quantum logic. Trouble is, it took a long time to find a pair, and it was done by implantation. And if you wanted to find another pair, you couldn't. You wanted to put 3 or 4, you couldn't. And again, it's because it's probabilistic. And in fact, there was a lot of money spent to try to solve that problem. And what was done was implantation of single nitrogen ions that were stored in the ion trap. You implanted one at a time with 1 nanometer precision into the diamond so that they can make a scalable array for a room temperature quantum computer. Trouble is, you can't let them stop at the surface or they won't be color centers. You got to let them go in, and when you go in, you can sort of see what's happening. They're not regular spacing anymore. And so they succeeded in getting the precision they wanted, but they failed in getting the final result. And again, that's a fundamental. You can't get around this. Okay, you can't simply improve the resolution here any better. You know, you're always stuck by this. So there's some serious fundamental limitations that you can't fix by just incremental improvements. And so to change the whole growth technique, this is the idea. And I'm not the only one that's had this idea. But the idea is basically, how do you grow good diamonds? You have a seed crystal that's high quality. You grow nice and slowly around it, and you get good quality diamond. So if you want to make nanodiamond, what's the seed? Okay? It's got to be something smaller than a nanodiamond, but a nanodiamond is really, really small. So the seed is a molecule. Okay, this is a single lattice unit of diamond. And it actually, we've substituted a nitrogen, so we can sort of make a nitrogen vacancy in that diamond where we want it. And then we grow a diamond around that by some reactive material. And the idea is the nitrogen vacancy, if you're lucky, will be in the middle, and there should be only one. And what this process does is it decouples the doping process from the growth. Okay, so now you can grow a very high quality diamond with no impurities at all, except what's started out in the seed molecule. Okay, so I actually worked at this for a number of years. And I first started with CVD and worked on that for maybe 6 or 7 years. It turns out that CVD involves a plasma, okay? And even when you've optimized the plasma conditions, you're doing a growth and etching in parallel, okay? And what's happening is that etching destroys the seed molecule. And so there's really no way this can work. I mean, I tried everything. I even tried flowing vapor plasmas. I tried downstream injection. I tried all kinds of things. And after about 10 years, I finally gave up. It couldn't be done. So what do? Well, fortunately, there's other ways to grow diamond. Most of the diamonds in the world are grown by high pressure. And if you look around it, everybody is trying to grow diamond now in the universities. But if you look around, everybody is doing CVD. Now, why is that? So I think it's perception. If the average professor looks at this equipment, they think, this isn't going to fit in my lab. And so they end up using CVD instead. And I sort of felt the same way when I first looked at this, is I'm not going to be able to get this to work in my lab. But then I found out that this is also high pressure. Okay, and this fits in the lab pretty easy. And in fact, one grad student can do it. So what this is a diamond anvil cell. It involves 2 diamonds back to back with a metal gasket. You put your reaction material in there, squash it down, and you get the same pressure as your high pressure reactor, and you can make it quite hot if you design it right. And what's better is you can watch, you can shine lasers in, you can look inside, you can watch things as they grow. And that's something you can't do in the other high pressure chambers. Being able to watch stuff happen really makes you progress a lot faster. So to make a long story short, we finally got the seeded growth technique to more or less work. So to prove it worked, we had to do 2 different seed molecules. One seed molecule with a nitrogen to grow nitrogen vacancies, and that's the standard nitrogen vacancy spectrum, NV0, NV-. Another seed molecule that had 2 nitrogens, but they're so close together they won't form a nitrogen vacancy. They'll form NVN, okay, and that's called H3, and that fluoresces in the green. So you can tell them apart. And so sure enough, we grow with this seed molecule, we get NV. We grow with this seed molecule, we get something that looks like the H3. Not exactly, but close to the H3. But the key thing is, there's no NVs. Okay, now, why that matters is if you're a crystal grower, every crystal grower will tell you that if you grow diamond and there's nitrogen anywhere in the growth mix, even trace impurities from the air, you're going to have lots of nitrogen vacancies. So in this growth mix, we actually put in a nitrogen releasing material to isolate the growth mix from the metal gasket. So we don't have just a trace of nitrogen, we got huge amounts of nitrogen. So we should be just swamped with nitrogen vacancies. But there aren't any. So why not? So here's my cartoon picture of why not. Remember I said slow growth? Crystals don't like to incorporate impurities. If you grow slow, the impurity won't go in there. If you grow fast, it gets stuck. Okay, so the process of putting impurities in also leads to defects. And so they're coupled. And so that's why you have to decouple. Okay, so the idea is to test this for the high pressure growth. We grow slow when the temperature is low. At high temperature, we grow fast because there's a lot more reactive carbon at high temperature than low temperature. So we did the experiment. Same seed molecule, low temperature and high temperature. I showed you this one before. No NVs. This is high temperature. At this temperature, the seed molecule decomposes. You got lots of nitrogen floating around. And sure enough, we get the NV, and we don't get this one anymore. Okay, so this is what every diamond grower in the world will tell you you're going to get. Okay, but we only get it at this temperature. At that temperature, we don't. And there's similar things. If you put silicon in the growth mix, for example, if you go to 1,100 degrees, you'll have a lot of silicon vacancies come out of your mix. You won't have to do anything. It'll just be millions of silicon vacancies. If you grow at a lower temperature, it doesn't matter how much silicon you put in the growth mix. You won't get any silicon vacancies. And we've seen that. Okay, so in the case of nitrogen, the temperature is somewhere between 400 and 650. And so this is a standard thing for crystal growth. So instead of having to purify a starting material, we simply grow at different temperatures. And we have dirty starting material, but we get very, very clean diamond. And to show you how clean it is, we use a nitrogen vacancy as a probe of the local environment. Now the NV has basically what was called a strain splitting. Actually, it's due to nearby nitrogens. It's due to charges. If there's other nearby nitrogens, you're going to get a splitting. And this isn't much of a splitting, but you can see it's flat top and the amplitude is down. So there is some splitting here, and these were grown in high temperature, so we think there are many nitrogens incorporated because it was grown fast. Here there should only be one from the seed molecule, and you see we don't get any of this split ODMR. We also did some charge stability studies. Nitrogens act as a source of electrons. When you pump the NV with blue, you ionize it. Okay, when you pump with green, it's not such a problem. And so you see there's a difference. But when you have more than one nitrogen, they act as sources of electrons. And for blue and green excitation, you get the same thing. So at high temperature, we got lots of nitrogens, so the charge is stable. Look, at low temperature, we think we have only one, and the charge is not stable. Okay, so it sort of looks like it's working. All right, so let's assume now that it is, and say where are we going to go next? Okay, where we're going to go next is to try to build things. One thing we want to do is to have a nitrogen vacancy with a carbon-13 nearby. And if this is a pure carbon-12 crystal, the lifetime of the quantum information is seconds. Okay, now you can find this occasionally in a bulk crystal, but if you want to make this at will, you need to have a way to control the spacing between the nitrogen vacancy and the carbon-13 when there's not very many carbon-13s. You want a carbon-12 lattice. And so if you take a seed molecule like this, where there's a well-defined spacing, grow a diamond around that, then you should get, in this case, a carbon-12 diamond, where there's only one carbon-13 in the whole crystal, but it's just the right distance from the NV. And so this is an approach to making a scalable quantum register, which can store information. And so that's one of the things we're trying to get a seed molecule to be able to do that. Another thing is, let's go back to that quantum computer, trying to place nitrogen vacancies with well-defined spacings. If you can make a molecule like this with a nitrogen at a well-defined position and you grow a diamond around this, you will then have a scalable array of nitrogen vacancies, which you can't get by any other technique. And so this is a way to do that. And of course, this molecule is even harder to get. But we did have a chemist give us this molecule. Okay. It's polymer with some adamantane stuck on it. And if you grow a diamond around that, you predict you'll get a polycrystalline. And sure enough, when we grow with that seed molecule, we get polycrystalline. And the number of crystal domains is about equal to the length of the chain. Whereas otherwise we get just a single crystal. Okay, so it looks like we're starting to get there, but there were no nitrogens on that, so we couldn't make any NVs. So hopefully the chemist will give us a nitrogen version quite soon. Okay, so that's the idea. Okay, so where do we go with this? Suppose we can make the quantum computer. Then we're going to put it in a nanodiamond, we're going to put it in the live cell, and we're going to use it to try to image. Okay, so instead of a single spin to image the protein, we're going to have a quantum computer to image the protein. We might put some reporter spins at different locations where these are going to be really small, maybe down to 1 nanometer. Where nitrogen vacancy wouldn't be stable, but the P1 center, or the nitrogen spin, will be stable. And then we'll be able to probe, maybe possibly do 3D imaging of this if we can get the quantum computer to work well. But of course, nobody's written software for such a computer, and they won't until we can show it. So we have to make it first. If you want to go farther, you can imagine taking a bulk diamond and putting some dopant at regular locations like a lattice. Say germaniums. Okay, now if you grow diamond over this, you'll have an array of germanium vacancies, and you can make a scalable quantum computer with that. Now this is not a new idea. People have tried this in diamond before. They've put things at well-defined spaces, and then they try to grow a diamond over it. But if you do it with CVD, you stick this thing in the plasma, and whatever was there on the surface is not there anymore by the time you really grow a layer over it. And so it doesn't work. However, this technique doesn't involve etching. It's only overgrowth, and so we should be able to do it. Okay, so of course, there's lots of choices for diamond emitters. And I told you about tin vacancy. We actually managed to get a hold of this molecule, but we've had trouble with the chemistry, so we haven't grown anything around it yet. We're also trying to get a hold of the silicon-containing molecule. But for the biological, there's a transparency window, and there's lots of interesting color centers in there. You know, there's the silicon vacancy, there's the nickel vacancy. I guess even some of the NV you can excite with red. So there's lots of choices, a lot of interesting things that we can look at. But each one needs a new seed molecule. And up till now, we've just used the seed molecules we can buy. Recently, we've had people making us some simple molecules. So we're just now getting started to look at other directions.
Phil, what's the significance of the letter B?
Oh, okay. We don't know for sure what there's a lot of interest in different charge states of the tin vacancy and the germanium vacancy. For example, maybe you want to have a positive charge state. If you would put a boron in the right place, you would force it positive. Okay, so that's the idea. So if you can get that into the seed molecule, that might be useful. Okay, so before I continue farther, I want to just point out that, remember I told you I want to get rid of the nitrogen vacancy, and the reason we couldn't get rid of it is because this fluorescence contrast for the different spin states was the highest that's been seen. Well, it turns out that there's been something higher. There's the so-called ST1, okay, which has 50% spin contrast. And then the one at Ulm, which is about 100%. And essentially, you get very strong fluorescence when the microwave is on, very little when it's off. Okay, and so that's much better than nitrogen vacancy, which means you'll get much, much better results. And in fact, there were some experiments showing the Stuttgart where they had some interesting quantum information that they could do with this center that they couldn't do otherwise. So it's very useful, except for one thing, nobody knows what this is. So if you want to make another one, you can't. All right? And so actually a number of people made things like this by accident, but still even making it by accident, even by implanting, still no one can figure out what it is. And so what I did is I got a hold of this crystal. It turns out there's one crystal that has the best color centers. And it's a natural diamond, of course, so you can't duplicate it. But I got a hold of it. I stuck it in the microscope. I found some really weird stuff. If you look in an ensemble, you have different regions to the crystal. Okay? In the bright region, you have the magnetic resonance with a negative contrast. In the dark region, you have positive contrast. You can see these are mirror images of each other. And you can see multiple lines, so there's probably more than one color center that's very similar properties. Slight differences between them. Turn on the magnetic field, and the third one pops up. And an extra one pops up. And so you can sort of imagine what's going on. You can say, well, this case must be a triplet ground state like the NV. This must be a singlet ground state like the ST1. But it looks like the same color center because they're mirror images. And they're in the same crystal, just different regions of the same crystal. So somehow the local environment is changing which state is, whether the triplet is ground or whether the triplet is metastable. And the important thing about this is this was an ensemble measurement. All the other measurements of things like ST1 were made on singles. And so you get this crystal, you search through the crystal, you find a couple fluorescent spots, you see this beautiful result, but you don't know what it is. And because you only see a few of them, you're talking about parts per trillion concentration of something that's making this. So try to find part per trillion of something in a crystal. This is not a part per trillion. This is ensemble. So that means there's going to be lots of them in the crystal, and we have a chance to find some. And so what do? Well, I annealed the crystal, and it got really bright, and it had a very well-defined line, and I said, great, now we know what it is. We just have to go to the book of diamond color centers, look up that line, and find out what it is. So I go to the book, and guess what? It's not there. So this is an unknown material that's never been reported in diamond before. And so now we have to try to find it, and the way we're finding it is we're implanting other things to try to see what's most like it. we're thinking perhaps a calcium or something else. We're not really sure. But we're in the process of implanting many things. We have crystals that are positive doped and neutral, and we're implanting many things from the periodic table. We're trying to narrow this down. And eventually, I think we're going to find it because, well, I mean, we have this crystal which has a reasonably large amount. We analyze what's in it, and we have some idea what to implant. Okay, so before I move on to some other things, let me tell you a little bit about some of the biological applications. I wasn't sure what to show here because it's a broad audience, but this is some experiments we did with tagging bacterial phages, where we stuck a diamond to a bacterial phage. And the idea is here, when the phage infects bacteria, the fluorescence from the diamond tells you which bacteria is infected. So if you have a bad bacteria, you can find it in a large ensemble of good bacteria. And it's very important for food safety. So that's one of the applications. Of course, you can see by looking at the picture that we need to make our diamonds a lot smaller. And in fact, we're going to try to get them to be even the size of the legs on the phage. Other things you can use diamonds for? Temperature sensing, okay? Turns out there's lots of ways to sense temperature. There's a lot of interest in sensing sub-wavelength things, or subcellular organelles. But what happened is that someone published a paper saying that the results up till now are incorrect. And they're incorrect because the temperatures people have been reporting are thermodynamically impossible. There's not enough fuel in the cell to maintain those temperatures. So they say it must be something else. And you think about it for a while, and how do you refute this? How do you prove that it's not something else? Okay, so after a while, it occurred to us that you simply have more than one technique. So here's a bovine embryo, which we inject, and we put different types of particles. We put diamonds, which have nitrogen vacancies, nickel vacancies. We also put some upconversion particles. And all these have different responses to temperature. But the key thing is there are different physics for each of these. Okay, if there's different physics, then what confuses one sensor won't confuse the others the same way. So if the temperature you measure with these agrees, then you know it's temperature and not something that's masquerading as temperature. And so we're able to show that well, at least we did for these two, show that they get the same temperature within their precision. Of course, once you start working with upconversion particles, you find out that they're really useful for a lot of things. And one of them is imaging things that are fluorescent. So many years ago, I decided to use nanodiamonds to image neurons in roaches. And I got a hold of some roaches. We injected some nanodiamonds, and we put them under the microscope. We said, wow, we're going to look at the brain. And it turns out we couldn't see the nitrogen vacancies because there was so much fluorescence from the roach brains that it was invisible. However, if you use these upconversion particles, what they are is they basically have many intermediate levels. You excite in the infrared, and you have an intermediate state so you can get visible emission with infrared excitation, so there's no fluorescence, right? Because all the fluorescence would be to the red, but this emission is to the green. So you can see things like the green spots are the particles. This is all the fluorescence from the autofluorescence from the biological system. You wouldn't be able to see single particles in there, but you can see single upconversion. And so these are really useful.
So what exactly do you mean by upconversion?
Upconversion, when we put infrared in, we get visible out. So you put in 2 photons of infrared, usually 980, and you get out something around 525, 550. Of course, these types of upconversion particles are very interesting for quantum information in the sense that if you have an efficient emitter for the excited transition, you can even see singles. Okay, this was shown in basically a single crystal or basically single praseodymium doped YAG. Of course, this was unfortunately in the UV, but it's possible to see single emitters under these conditions. And so there's actually a group in Stuttgart that's exploring all the different options for this now, but this was, again, room temperature. We can also use them in plants. One of the experiments we want to do is monitor plant health in the field, tell if the plant is stressed or not. So what we do is we put nanoparticles in the water, we water the plant, and it gets up into the roots, the stems, and the leaves. And we can see the particles in the plant. And the reds are autofluorescence. So you can definitely distinguish. And once you have them in the plant, you can start to measure things like how much glucose is being produced, or what's the temperature, things like that. You can monitor the plant health even from a long distance, because you can imagine having a sunlight filter, right? Because this is your exciting infrared. Okay, so to make this really work, one of the disadvantages to upconversion particles is that their quantum efficiency is not very high. So it tends to be 1% or less. Okay, and when you go to a nanoparticle, it tends to be worse because most of these upconversion particles are quenched by water. So of course, the ones we use are not so quenched, but they are somewhat quenched. So how do we get around this problem of low quantum efficiency? We decided the best way to get around it was to do a FRET interaction. FRET is fluorescence, resonance, energy transfer. If you have something that emits at a certain wavelength, like an upconversion particle, and something that absorbs at that same wavelength at the NV, and they're close together, you can transmit the excitation directly, much faster than ordinary spontaneous emission, and then the quantum efficiency will be determined by how fast this nitrogen vacancy decays, and so you can, in principle, get it up to 100% quantum efficiency, plus you could do magnetic resonance imaging with upconversion. So this is kind of what we did. We tried everything, okay, to get nitrogen vacancy close enough to an erbium. So the most recent thing we tried was to take an erbium-doped phosphor, and the idea is to make this small enough, maybe a couple nanometers, so that you can, nitrogen vacancy on one side will see all the erbiums. And then we basically grow a diamond around this, and we want the nitrogen vacancies to be on the inner surface. And so the approach to this was to put these diamondoid molecules, anchor them to the surface, and then try to grow a diamond around this. And here's a better picture. Right, this is actually the molecule we used. Unfortunately, the commercial particle we used had some oxygen, and so that turns out that's a problem, but that was the goal. And what we got, well, okay, we got upconversion particles surrounded by diamond. Okay, and if we look with the green excitation, we see basically, we see the erbium peaks, we see the diamond Raman line at the same time. And after we do irradiation and annealing, we see nitrogen vacancy in the erbium peaks at the same time. We see the ODMR to know that we have nitrogen vacancy. What we don't see is when we do the upconversion, we don't see the NV. So the NVs are not as close to the erbiums as we thought they were. And like I said, we think that's due to our chemistry for the linker chemistry. So we're going to have to change this. But at least we're able to grow the diamond shell around the upconversion. Now another thing you might wonder is if we actually want to put nitrogen vacancies within a few atomic layers of this upconversion, will they still be nitrogen vacancies? So it comes to the question of how shallow can a nitrogen vacancy be and still be a nitrogen vacancy? Okay, so we did some experiments making ultra shallow NVs. Now typically if you make an NV, people do it in ultra pure crystals mostly. And when you get shallower than about 3 nanometers, it blinks and disappears, blinks out. So what we did is we took a layer of nitrogen-rich diamond, and we implanted the ultra-shallow layer of just a couple of nanometers. And these all made really shallow NVs. And we look at the ODMR, it's quite good. Sometimes narrow, sometimes not. And to show that the depth was shallow, we put a black hole quencher. Black hole quencher is a dye that works by FRET coupling. So the fluorescence from the nitrogen vacancy goes right into the dye and doesn't emit. Okay, the range of this is about 3 nanometers. So if the nitrogen vacancies are farther than 3 nanometers from the black hole quencher, they're not quenched. But you can see here they are being quenched. We've looked at lots of other layers, ultra shallow layers, and they're never quenched by a black hole. Only these layers that we make are quenched. And if you look at the optical spectrum, you'll see there's a difference. Okay, the phonon sideband structure has changed when you get very shallow. But they're still NVs, they still got good ODMR. So it is possible to make a super, super shallow NV, less than 3 nanometers. And this is the signature, it's got a different phonon sideband spectrum. Okay, now you might have noticed that some of these particles were actually, well, okay, this has to do with scaling. We want to scale up, okay? And so high pressure is in principle, you could get a lot of, you could scale up at high pressure, but you know, we don't have a big press. So we want to find a way to scale up without a big press. Okay, so it turns out that if you have a very small diamond, below 7 nanometers, it's the most stable form of carbon, even with atmospheric pressure. Okay, the trouble is when you get bigger, it becomes something else. So most of what we do, if we want to be less than 5 nanometers, we shouldn't need the pressure at all. We should be able to grow with atmospheric pressure. However, what we found, I don't know if you noticed this, but we found that here we got things that are much bigger than that, okay? And these were growing at atmospheric pressure. And so the thing is, if you look at previous literature, you'll find out that when you grow at atmospheric pressure, in the range of 5 to 7, you get diamond, 8 to 13, you get N-diamond, above that is graphitic. So we're grown way past the limit of stability of diamond, and we haven't got graphite. So the question is, how can that be? Okay, and the answer is diamond is metastable. So if I take a diamond, okay, and I put it over here on the table, that's not the most stable form of carbon. But if I come back tonight, it's still going to be diamond. If I come back next year, it's still going to be diamond. If I come back 100 years, it's still going to be diamond. Even though it's not the most stable form of carbon, it's very, very metastable. And so in principle, if you can grow at a temperature, a low enough temperature, but where this doesn't convert spontaneously to graphite, you can grow diamond without pressure. So what is that temperature? Well, 1500 degrees turns diamond into graphite very quickly. But since we're growing, we care about the surface, right? If the surface, even the topmost surface layer, if that's graphitic, we're going to grow graphite. So what's the temperature where the surface converts? And that turns out to be 900. Okay, 900 C, the hydrogen comes off, so it's not hydrogen terminated, and the dangling bonds reconstruct, give you sp2 bonding, and from that point on, graphite. And that's the reason that nobody, and basically everybody that's ever grown diamond grows above 900. Okay, so nobody's ever seen diamond grow bigger than about 7 nanometers because they grow at high temperature. So we grow well below that temperature. And so we grow with diamonds metastable, and we think that's why we can see it. Okay, so this is just some of the small diamonds we get in this shows the electron microscope. So the key here is to make them small. And actually, it turns out because we don't need pressure, we can even grow them in the electron microscope. So this was just a 700 degrees C for 1 hour, and we got some fairly small diamonds. So they weren't big like the ones I showed you before, but at least we can get diamonds. And we can irradiate these afterwards and anneal them and show that we get nitrogen vacancy so that they really are diamonds. And so when we first saw this in the vacuum, we said, wow, we can grow diamonds in the vacuum. But then we said, oh, the electron beam must have done it, right? Because there are lots of papers where people have an electron beam, they irradiate diamonds, and they radiate graphite, and converts back and forth. So it must be the electron beam. So we did a control experiment where we took the same growth mix and we put it in a tube furnace. Okay, in the tube furnace, there's no electrons. We basically had to mix some graphene flakes because the grids were carbon grids. And it turns out the carbon suppressed evaporation of our growth material. Carbon is bonds very strongly to organics. If we didn't put that, then at the temperatures we grow, the growth material would have boiled off instantly. But the graphite holds it, so we used some graphene flakes, and sure enough, we got strong diamond Raman lines coming out. We implanted an anneal, we got good nitrogen vacancies. We even did the seeded growth, where we have our 2 different seed molecules, and we get the red and the green the red and the green fluorescence. Okay, and so at least for the small nanodiamonds, we don't need pressure. We think that for the bigger ones, we're probably also not going to need pressure once we understand. Okay, so how am I doing on time? Because I have
Got about
7 minutes. Okay, so I have a series of slides about all the things that go wrong with seeded growth. So I'll save those for the questions and answers, and I'll go straight to my conclusion now. Basically, I have a series of slides saying all the stuff we don't know about seeded growth, all the stuff that doesn't work like it's supposed to. So I'll kind of skip forward on this now and go straight to the conclusion. Okay. And so what I showed you is that we have a way to engineer color centers by using seed molecules. And the idea is we decouple the growth from the color center creation so we can make high quality diamond. without having to worry about trying to incorporate the impurities because they're in the seed molecule. And eventually we want to use this to do things like make quantum computers in the live cell, work inside a live cell. We want to do single biomolecule imaging, and we want to make, once we identify this high contrast magnetic resonance center, we want to make a lot of those. And of course, there are lots of other things this can be applied to. For example, this is a molecule that's a single crystal, a single lattice unit of silicon carbide. So we can start to look at other materials. So this has been made, so we can get that. In fact, you can grow silicon carbide quite easily, it turns out, even when you don't want to. But if you have a seed molecule, you can control what you substitute, and so you have control over the vacancies or the color centers that you create. And if we're lucky and things keep going like they're going, we might not need this anymore. So that's kind of, all right, so that's enough for now.